Good evening and welcome to our second course on phase space analysis, plotting phase diagrams, and in general understanding solutions in terms of phase space. As a reminder, in this course we're only going to look at this theory in one dimension. So our phase space will actually be a line. And this is the general method for analyzing one-dimensional dynamical systems that we described and gave examples of last time. So we're looking at the equation y prime is equal to f of y, which is the general form of an autonomous first-order ordinary differential equation in explicit form. So y prime is equal to f of y. And f can be any reasonable function of y. So a continuous and differentiable function of y, like y prime is equal to sine of y prime is equal to e to the y prime is equal to y squared times 1 plus natural log of y, etc. But we want the function to be defined on the whole real line, maybe, so not the last example. Okay, so on a vertical line, the first thing that we do is we draw the vertical line itself. Second step is on this vertical line, we figure out where the zeros of f are. So we solve the equation f of y0 is equal to 0 and find all the roots y0, all the zeros of the function f. The reason for that is that the points y0 such that f of y0 is equal to 0 will give constant solutions of our equation, which are called equilibria, or stationary points. So the functions y of t is equal to y0 are constant solutions of our equation. Second step is these points divide the real axis into intervals. From minus infinity to the smallest point, then from the smallest point to the next point, and so on and so forth to the highest point, and then from the highest point to plus infinity. So, for example, if we have two equilibrium points, these will divide the real axis into 3 intervals. If there are infinitely many stationary points, the situation is a bit more complicated, but in most cases, our analysis can also handle that. Okay, so consider one interval between two stationary points, or between the last stationary point and plus infinity, or between minus infinity and the first stationary point. So stationary points are zeros of f. So between any two stationary points, f has constant sign because so if f took both positive values and negative values on one of these intervals, then since f is continuous, f would have to also take the value 0. And this would correspond to a stationary point that we have missed in this. So assuming that we didn't miss any stationary point, then on each interval, f will have constant sign. And then we need to place an upward arrow on the interval if the sign is plus, and the downward arrow if the sign is minus. So this will describe the behavior of all the solutions that take values in that interval, namely on an interval on which f is positive, all solutions that take values in that interval will be increasing, and on an interval on which f is negative, all solutions will be decreasing. Next, we look at the equilibrium points themselves. So each equilibrium point has two neighboring arrows from the two intervals that border it. And if both of these arrows point towards the equilibrium point, then it is called a stable equilibrium or a sink. If both arrows point away from it, it is called an unstable equilibrium or a source. And if one of the arrows points towards it and the other one points away from it, then it is called a semi-stable equilibrium or a node. With this, we have almost completely described the behavior of all solutions to our equation. So by looking at the phase diagram, we can understand the behavior of each solution without actually having computed it. Just as a reminder, this sort of analysis applies to autonomous first-order equations. So equations of the form y prime is equal to f of y. So these are the equations in which the independent variable does not appear. So if y is a function of x, or if y is a function of t, or whatever, then the equation still only contains y prime and y. For example, y prime is equal to y is an autonomous equation, or y prime is equal to y squared plus sine y is an autonomous equation. On the other hand, we cannot do this sort of phase space analysis for non-autonomous equations, which are those where the independent variable appears in the equation. So if y is a function of t, then t is called the independent variable, and then y prime is equal to y plus t is not an autonomous equation because it has t in it. And similarly, y prime is equal to x squared plus sine y is not an autonomous equation because it has x squared in it. It turns out that in order to do a phase space analysis of a non-autonomous equation, then we need to increase the dimension of the phase space by 1. So a non-autonomous equation can be converted into an equivalent autonomous system of equations by increasing the dimension of the phase space by 1. So this means if we start with a phase space of dimension 1, if we also count for the variable, then we end up with a phase space of dimension 2. So the phase space for a non-autonomous equation or system of equations always has at least dimension 2. So our method that we are describing here today only works for autonomous first-order equations. Okay, so this is a typical example for which we can plot the phase diagram using the method I just described. Y prime is equal to e to the y times y minus 1 squared times y minus 2. So let's go through the 3 steps. First, we try to find the equilibria, the equilibrium solutions of the equation. So in order to do that, we solve the equation e to the y times y minus 1 squared times y minus 2 is equal to 0. So if a product is 0, this means that one of the factors in the product must be 0. E to the y can never be 0, so either y minus 1 squared is 0 where y minus 2 is 0, which means either y is equal to 1 or y is equal to 2. So these are the two equilibria, these are the two constant solutions of the equation. Y of t is constantly 1, or y of t is 2. So on our real axis, we plot the two numbers, 1 and 2. And these divide the real axis into 3 intervals, from minus infinity to 1, from 1 to 2, and from 2 to infinity. Then we can check either by giving values or by looking at the signs of all the factors in the product. We can find the sign of f on each interval. So on each interval, f will have constant sign. For example, in order to find out what's the sign of the function f on the interval minus infinity 1, we could give to y the value 0, because 0 is in the interval minus infinity 1. And then we see that f of 0 is e to the 0 times 0 minus 1 squared times 0 minus 2, and this ends up being minus 2. So it's a negative number. Or another way that we can look at it is what happens if y is a number that's less than 1, then e to the y is always positive. Y minus 1 squared is a square, so it's positive. And if y is a number that's less than 1, then y minus 2 will be negative. So we have positive times positive times negative, and this works out to negative. And in a similar way, now let's look at the second interval from 1 to 2. So if y is a number between 1 and 2, then e to the y is still positive. Y minus 1 squared is a square, so it's positive. And y minus 2, well, if y is a number between 1 and 2, y minus 2 is still negative. So f is also negative on the interval from 1 to 2. And finally, if y is bigger than 2, then we see that all the factors in this product are positive. So again, e to the y is positive, y minus 1 squared is positive, and if y is bigger than 2, then y minus 2 is also positive. So everything is positive. Okay, so f is positive on this third interval. So then on the first interval, we put a down arrow, a downward pointing arrow, because we established that f was negative on the interval from minus infinity to 1. On the second interval, we again put a downward pointing arrow, because f was also negative on the interval from 1 to 2. And finally, we put an upward pointing arrow on the last interval from 2 to infinity, because f was positive on this interval. So this concludes the second step. And the third step is the stability of the equilibria. So there are two equilibria in this problem, 1 and 2. And we look at the arrows around 1 and around 2. So around 1, there are two arrows, one that points away from it, so the one that goes from 1 to minus infinity, and the other one that points towards it, the one that goes from 2 to 1. So this means it's a semi-stable equilibrium, because one arrow points towards it and one arrow points away from it. What about the number 2? So the number 2 is a source or an unstable equilibrium because both arrows point away from it. So there's the arrow that goes from 2 to 1, and there's the arrow that goes from 2 to infinity. So this means it's a source or an unstable equilibrium. So practically this means that if we start our problem with even a very small deviation of 2, so if our initial condition were y of, let's say, y of 10 is equal to 2.001 or 1.999, then the solution will very soon deviate from 2. So it will go away from 2. On the other hand, 1 is semi-stable, which is also called a node, because as we see, it is stable in one direction. So as you come upwards, so if you put the initial data to be, let's say, 1.01, then this will be driven towards 1. But if you start from below 1, then your solution will be driven away from 1 towards negative infinity. So this is what makes it semi-stable. All right, so this concludes our exploration of the phase diagram. And note that the e to the y factor does not actually affect the phase diagram. So if instead of this we had the equation y prime is equal to y minus 1 squared times y minus 2, it would still have the same phase diagram. Okay, so once again, this is how we draw the phase diagram. First, we draw a vertical real axis from minus infinity to plus infinity. Then on this phase diagram, we figure out where the equilibria are. So we compute the zeros of f of the right-hand side of the equation, which in this case are 1 and 2, and we plot these points on the vertical real axis that we just drew. And you have to be careful here so that you draw them in order. So if the zeros are 1, 3, and 2, you should still draw them in the order 1, 2, 3. The second step is by one method or another, we find out what sign f has on each of the intervals of the real axes that are separated by the points 1 and 2. So the points 1 and 2 separate the real axis into 3 intervals, minus infinity 1, 1, 2, and 2 infinity. And we have to find out the sign of the function f, whether it's positive or negative on each interval. And in this case, it turns out that it's negative on minus infinity 1, negative again on 1, 2, and positive on 2 plus infinity. And then we put arrows on each interval. So downward arrow if the sign is negative, and an upward arrow if the sign is positive. And finally, for the last step, the stability of equilibrium, we look at the same diagram that we just drew again, without making any change, but we look at it from a different point of view. So instead of looking at intervals, we look at the 2 points, or the 2 equilibrium points, and we look at the direction of the arrows around each equilibrium point. So if both arrows coming out of an equilibrium point are going outward, like for 2, then 2 is a source or non-stable equilibrium. If one arrow goes in and another goes out, like for 1, then it is a semi-stable equilibrium or a node. And there is this third kind of equilibrium, which is not depicted on this diagram. If both arrows are going towards the point, then it is a sink or a stable equilibrium. Next example, let's consider the equation y prime is equal to y times y squared minus 1. So let's plot its phase diagram. The first step is we identify the equilibrium points for the equation. So we want to solve the equation y times y squared minus 1 is equal to 0. Well, this means either y is equal to 0 or y squared minus 1 is equal to 0. So either y is equal to 0 or y is equal to plus or minus 1. So there are three equilibria, minus 1, 0, and 1. And we plot them on this vertical axis, minus 1, 0, and 1. So now these 3 points divide the axis into 4 intervals. From minus infinity to minus 1, minus 1, 0, 0, 1, and 1 infinity. On each of these 4 intervals, the function will have constant sign. And this is one way, again, to find out the sign of the function. Namely, we just pick one point in each interval, and we test the sign of f at that point. So on the interval minus infinity minus 1, for example, we can pick the point minus 2. And f of minus 2 is minus 6. So f is negative, where f again is y times y squared minus 1. And then on minus 1, 0, we can choose any point between minus 1 and 0. For example, let's choose minus 0.5. And then f of minus 0.5 is 0.375. So this is positive. It's a positive value. This is all that we care about, the sign of the value. We don't care about the value itself. Well, on the interval 0, 1, again, the natural choice is 0.5. And f of 0.5 is minus 0.375. So it's a negative number. And on the interval 1 infinity, again, we can choose any number we want. So let's choose 2. F of 2 is 6, which is positive. So this one will have an upwards pointing arrow. So now let's actually plot the arrows on each interval. On the first interval, there should be a downward pointing arrow because we had a negative value. On the second interval, it's an upward pointing value because we had a positive value, 0.375. On the third interval, it's a negative value, so it's a downward pointing arrow. And on the last interval, between 1 and infinity, it's a positive value, so it's an upward pointing arrow. And again, now the phase diagram is complete, and this almost completely describes the behavior of all solutions to the equation. And part 3, we are particularly interested again in the stability of the equilibrium points. Now we have three equilibrium points, -1, 0, and 1. From -1, both arrows near -1 are pointing outward, so -1 is a source, or an unstable equilibrium. For 0, both arrows near 0, so both arrows neighboring 0, are pointing towards 0. So this means that 0 is stable, or a sink. And at 1, both arrows pointing away from 1, both arrows look like they are pointing away from 1, meaning that 1 is again a source or an unstable equilibrium. This concludes our phase space analysis of this equation. Okay, now let me give for a change a more applied example, namely the logistic equation that we studied in the application section. As I said before, this provides a more realistic model for population growth. The equation is y prime is equal to ry times 1 minus y over k, where r is the growth rate and k is the carrying capacity of the environment. So the actual growth rate is r times 1 minus y over k, because when y is near the carrying capacity of the environment, then the growth is actually near 0. And in the logistic equation, r and k are positive numbers because r corresponds to some growth rate and k is the carrying capacity of the environment. Both logically should be positive numbers. The first step is we try to identify the equilibria for the logistic equation. So we solve the equation ry times 1 minus 1 over k is equal to 0. So since r is a positive number, this means that either y has to be 0 or 1 minus y over k has to be 0. So y is 0 or y is equal to k. So these are two constant solutions to equilibria of the equation. Y of t is always 0 or y of t is always k. The first case corresponds to the situation where the population is 0, so then it cannot grow, it cannot decrease, it will always be 0. And the second case is y of t is always k. So when the population is at exactly the carrying capacity of the environment, then it has no room to grow and it has no reason to decrease. So it will always be equal to k. Since there are 2 points, they split the real axis into 3 intervals: minus infinity 0, 0k, and k infinity. And let's try to find the sign of the function f of y on each of these intervals. So on the interval minus infinity 0, this means y is less than 0. And then let's look at the product ry times 1 minus y over k. So r is positive, y is negative because it's in the interval minus infinity 0, and 1 minus y over k is 1 minus a negative number, so it's again positive. So we have positive times negative times positive, therefore the product is negative. So the arrow should be downward. Next, let's look at the interval 0k, where we have, let's see. So R is positive again. Now Y is positive because it's between 0 and k, so it's a positive number. And 1 minus y over k is again positive because y being between 0 and k means that y is less than k. So y over k is less than 1. So 1 minus 1 over k, y over k is positive. So we have the product of three numbers. All three numbers are positive. Therefore, the function is positive. So the arrow should be upward. Finally, when the interval k infinity, so let's see. So again, the function is ry times 1 minus y over k. R is positive. Y is positive because it's a positive number bigger than k. And 1 minus y over k, well, now y is bigger than k, so y over k is bigger than 1. So 1 minus y over k is less than 0. So now we have the product of two positive numbers and one negative number. So this means overall the product is negative and the arrow should be downward. Right. So this completes our phase diagram. We have put arrows on each interval. This is downward, then upward, then downward again. And for part 3, we should look at the stability of the two equilibria. First, we look at 0. The arrows in the neighborhood of 0 are going away from 0. So there's the arrow above 0 is going towards k, and the arrow below 0 is going towards minus infinity. So this means that 0 is an unstable equilibrium, which is called a source. What about the point k? Both arrows in a neighborhood of 0 point towards k, so the arrow goes from plus infinity towards k, above k, and the arrow goes from 0 to k, below k. So both arrows are pointing towards k. This means it's a stable equilibrium, otherwise known as a sink. So this means that if we start with a population that is even slightly different from 0, then the population is going to very rapidly go away from 0. Well, in the application, the population can only be positive. So this means if we start with a positive population, even if it's a very small population, it's going to grow away from 0. It's going to become larger. This is what makes 0 an unstable equilibrium. So if the population is originally 0, it will forever remain 0. But if it's even slightly different from 0, then it will grow away from 0. Whereas k is a stable equilibrium, this means that if we start with a population that's not quite equal to k, but maybe very slightly different from k, then the population is going to go back to the equilibrium K. So if population is more or less in equilibrium, but maybe there is some circumstance that makes it deviate from equilibrium, like there's some extra food that was not foreseen by the equation, or there is some extra predator that was not foreseen by the equation. And so the population is pushed away from equilibrium, then it will have a tendency to go back towards equilibrium. This is what it means that K is a stable equilibrium. All right, this is the final example for today. Y prime is equal to minus 2y times y plus 1 squared times y minus 2 times y minus 7. And for all of these, let's note that even if the equation looks rather complicated, and even if computing the integral is more difficult, plotting the Phase diagram is always rather straightforward and gives us a general idea of the solution's behavior without actually getting into the computations, without actually computing the solutions. So let's do the phase analysis, phase space analysis of this equation. The first step is again to find out the equilibrium points. So we need to solve the equation minus 2y times y plus 1 squared times y minus 2 times y minus 7 cubed is equal to 0. So if this product is 0, this means that one of the factors must be 0. Minus 2 cannot be 0, so either y is 0, which means y is equal to 0 is a constant solution, or y plus 1 squared is 0, which means y is equal to minus 1, or y minus 2 is 0, which means y is equal to 2, or y minus 7 cubed is 0, which means y is equal to 7. So we found 4 equilibrium points, minus 1, 0, 2, and 7. These 4 points divide the real axis into 5 intervals: minus infinity, minus 1, minus 1, 0, 0, 2, 2, 7, and 7, infinity. So in order to plot the phase diagram, we have to compute the value, not the value, the sign of f on each of these 5 intervals. And we can again do this by giving values. For example, on the interval minus infinity, minus 1, let's pick, for example, y equal to minus 3, and find out the sign of f at minus 3. So we get f of minus 3 is equal to 120,000, which is a positive number, so the arrow is pointing up. But instead of computing these very large numbers, another thing we can do is compute the sign of each factor, since f is given by a product, and then count how many minuses and how many pluses we have. So when we plug in -3, for example, we get -2 times -3 times -3 plus 1 squared times -3 minus 2 times -3 minus 7 cubed. So of these factors, -2 is negative, -3 is negative, -3 plus 1 squared is positive, -3 minus 2 is negative, and -3 minus 7 cubed is again negative because 3 is an odd power and -3 minus 7 is a negative number. So overall, we had 4 negative numbers and 1 positive number. So product of 4 negative numbers and 1 positive number is positive, because negative times negative is positive. So in general, if we have an even number of negative factors, then the product is positive. Let's do this on the other intervals as well, either by actually computing the value of f or by just looking at the sign of each factor. We get the following conclusions. So on the interval -1 and 0, let's pick the point -0.5. F of -0.5 turns out to be 263 dot something, which is a positive number. On the interval 0, 2, let's pick 1 in the interval 0, 2. F of 1 is -1728, which is a negative number. On the interval 2, 7, let's pick the point 3 between 2 and 7. So F of 3 is 6,144, which is a positive number. And on the interval 7 infinity, for a change, let's pick number 9. So F of 9 is -100,800, which is a negative number. So on the first interval, we had upward pointing arrow. On the second interval, we again had an upward pointing arrow. On the third interval, we had a downward arrow. On the fourth interval, we had a positive value, so we had an upward arrow. And on the last interval, we again had a negative value, so again we had a downward arrow. This really concludes the phase diagram. And now let's again try to interpret it and read from it whether each equilibrium is stable or unstable. So -1, which is the smallest equilibrium, well, we have one arrow pointing towards it. The arrow that comes from -infinity points towards -1, and one arrow pointing away from it. So the arrow that goes from -1 to 0 points away from it. So -1 is a node or a semi-stable equilibrium. Next, the next equilibrium point is 0. So both arrows in a neighborhood of 0 point towards 0. So there's the arrow that comes from -1 to 0, and there's the arrow that comes from 2 to 0. This means that 0 is a stable equilibrium or a sink. Next equilibrium is 2. So both arrows near 2 are pointing away from 2. One is pointing towards 0, and the other one is pointing towards 7. So this means that 2 is an unstable equilibrium or a source. And finally, the number 7 is also an equilibrium. This means that the solution y of t is equal to 7 is a constant solution of the equation. And we look at the phase diagram again and see that both arrows are pointing towards 7. So there's the arrow that goes from plus infinity towards 7, and the arrow that goes from 2 towards 7. So this means that 7 is a sink or a stable equilibrium. And let me underline again that the phase diagram, so this phase line, can be used to understand the behavior not only of equilibria, like -1, 0, 2, and 7, but also of solutions that live on the intervals between the equilibria. For example, a solution that starts with an initial value between 2 and 7, let's say your initial condition is that y of -1 is equal to 5. So 5 is a number between 2 and 7. Well, from the phase diagram, we see that there's an upward arrow on the interval 2, 7. So this means that a solution whose initial value is 5 will be increasing and will asymptotically approach 7 as time goes to plus infinity. So every solution that lives on an interval between two equilibria, as we'll see very soon, exists for all time and has horizontal asymptotes as t goes to plus infinity and as t goes to minus infinity. The behavior of solutions below the smallest equilibrium or bigger than the largest equilibrium is not completely determined by the phase diagram, but we can still tell a great deal about them by looking at the phase diagram. All right. So this concludes our examples of plotting the phase diagram in one dimension. These examples are quite representative. There are a few more complications that can arise, for example, when there are infinitely many equilibrium points on the real axis or things like that. But overall, when the right-hand side function is sufficiently nice and smooth, then this is how the analysis goes. So one-dimensional phase space analysis is relatively straightforward. It consists in a number of steps that we have looked at. So you can do these steps and analyze the phase diagram of any first order autonomous equation. And almost all the important details about the problem are captured in this diagram. There are no very complicated solutions. For example, there are no periodic solutions. In fact, if we look at the phase diagram that we drew, every solution is either constant if it's an equilibrium, or it's increasing if it's on an interval with an upward arrow, or it's decreasing if it's in an interval with a downward arrow. So in all three cases, once a solution leaves its starting point, it cannot return there. So the only periodic solutions are the constant solutions, which actually never leave their starting point. In higher dimensions, there are more interesting trajectories and more complicated behaviors that a solution can have. However, in one dimension, these are all the possible behaviors. The one-dimensional and two-dimensional phase diagrams are easier to understand than more general phase diagrams because plane geometry and one-dimensional geometry are much simpler than geometry in higher dimensions. The one-dimensional theory we have almost completely described today. The two-dimensional theory is somewhat more complicated, but still there exists a satisfactory general theory in two dimensions. The main theorem is called the Poincaré-Bendixson theorem, and with its help, one can completely classify all the possible orbit types in two dimensions. So I am referring to systems of two autonomous first-order ordinary differential equations. Discrete systems, so systems that are not described by ordinary differential equations, are somewhat more complicated, and this is not what I am talking about today. Okay, so let's state and prove a theorem about one-dimensional phase diagrams so that we know that all this discussion that we had was based on rigorous theory. So this theorem characterizes the behavior of solutions that live between two equilibrium points. It says the following: let f be a continuously differentiable function, meaning continuous with continuous derivative, from R, taking values in R. So f is real valued and f is defined on the whole real axis, such that f of A is equal to f of B is equal to 0. So A and B are two equilibria, and f of Y is non-zero for all Y between A and B. So A and B are successive equilibria. There is no equilibrium point between A and B. Now let's consider a solution of the equation y prime is equal to f of y with the initial condition y of t0 is equal to y0, where y0 is a point between A and B. So the starting value of our solution is y0 in the interval between the two equilibria A and B. And the value of t0 is irrelevant. It turns out that the solution will behave the same way regardless of at what time we set the initial condition. Then the solution y of t exists, is unique, only takes values within the interval a, b, so y of t will never be less than a or bigger than b, and is monotone, so y is either always increasing or always decreasing, and its interval of existence is the whole real axis from minus infinity to plus infinity. The proof is relatively straightforward, and it's based on the existence and uniqueness theorem for solutions to this ordinary differential equation. So because the function f is continuously differentiable, solutions to these sorts of initial value problems, y prime is equal to f of y and y of t0 is equal to y0, exist and are unique. So for each t0 and y0, there exists a unique solution. Based on this, let's prove that the solution y of t only takes values between a and b. If y of t ever became bigger than a or less than b, since our starting value y0 is in the interval ab, then by continuity, more precisely by the intermediate value theorem, the solution would have to take the value a or b at some point. So if it starts below a and then eventually gets above a, by continuity, it has to go through the value a. And if it starts above b and ends up below b, then again by continuity, somewhere in between, it has to take the value b. Now we want to prove that neither of these things can happen. So in order to obtain a contradiction, suppose that y actually eventually became bigger than a, so at some point took the value a. Then let that moment in time be called t1. So y of t1 is equal to a. Then let's consider the initial value problem. Y prime is equal to f of y, and y of t1 is equal to a. This initial value problem then would have two different solutions. One of them is the constant solution, y of t is constantly equal to a. Because a is an equilibrium, this means that y of t is equal to a is a solution of the ordinary differential equation. The other solution is the solution we are looking at, the one that had y of t0 is equal to y0. Because y of t0 is equal to y0, this means that this is another solution which is not constantly a. So it's not the same as the first solution. Since we found two different solutions to this initial value problem, this is a contradiction because we know that solutions to initial value problems for this equation are unique. So this contradiction shows that our original assumption was wrong, and in fact, y of t can never become bigger than a. And in the same way, using a similar proof by contradiction, we can prove that y of t can never take a value below b. So therefore, y of t is confined to the interval ab for the whole interval of existence of the solution. Next, by an argument we have not studied completely, as long as y of t remains in the interval AB, this guarantees its global existence. So this means that, first of all, it cannot blow up because it's always in this bounded interval between A and B. And secondly, because the function f, so in the equation y prime is f of y, since the function f is continuously differentiable on the closed interval a, b, this means that we can always keep extending the solution, the domain of existence of the solution y of t, by at least some fixed amount of time. So whenever we think we have reached the end of its interval of existence, we can add at least some fixed amount of time to its interval of existence. So in this manner, because the solution always remains between A and B, this ensures that the solution exists for all time. So it is globally defined. So in other words, its maximal interval of existence is from minus infinity to plus infinity. It is the whole set of real numbers. Finally, as I have mentioned before, since A and B are successive equilibrium points and f is non-vanishing, f is not zero on the interval AB, this means that f must have constant sign on the interval AB. If f had both positive and negative values within this interval, then again, since f is continuous on the interval AB, by the intermediate value theorem, if f were both positive at some point and negative at some other point, f would have to be zero at some point in between. And this point would be in the interval AB as well. And this is a contradiction because we assume that there is no equilibrium between A and B, that A and B are successive equilibrium points. So this means that f is either positive all the time on the interval AB, or it's negative all the time on the interval AB. If f were positive on the interval AB, then, so this means f of y is always greater than 0 for all y in the interval AB, plus then since y prime is equal to f of y, and since our solution only takes values in the interval AB, this means that f of y is always greater than 0 for our solution, so y prime is always greater than 0 for our solution, which means that y of t is always increasing. In the same manner, if f of y is always less than 0 in the interval AB, since our solution only takes values in the interval AB, this means that f of y is always less than 0 for our solution y of t. So this means that y prime is always less than 0, so y of t is always decreasing. You are not required to know the proof of this theorem for the exam, but this is the reason why phase diagrams work in one dimension in the manner in which we use them. The behavior of two-dimensional systems is more complicated than in one dimension. You can imagine that in 2 dimensions, for example, the trajectory of a solution can be a circle, whereas in 1 dimension, we have no circles. And in 3 dimensions and higher, the behavior can be, again, much more complicated. And one of the things that can happen in 3 dimensions or higher, but cannot happen for 2-dimensional systems of ordinary differential equations, is chaotic behavior. Poincaré was the first one who proved that a certain dynamical system exhibits chaotic behavior. This was tied to his investigations into the motion of planets and to the theoretical problem known as the three-body problem. So his conclusion put an end to certain hopes of obtaining an explicit solution for the three-body problem. Chaotic behavior means that, among other things, solutions to a certain system of ordinary differential equations or dynamical system are harder to predict because it can happen that for a very small perturbation of the initial condition, the behavior of the solution will be completely different. The introduction of computers later made it possible to study higher dimensional systems of ordinary differential equations more systematically using numerical methods. So certain behaviors were discovered in this manner and others were confirmed. And one of the pioneers in this field was Lorentz, who, starting from a model used for weather prediction, realized that chaotic behavior is important, including in the study of weather and weather forecasting. And he undertook a systematic study of chaotic behavior.